The force of friction in a little more detail. First of all, let's give a little bit of a definition. Let's write it like this. Friction is a reaction force. And it always opposes motion. It always works against moving. In other words, it's a reaction force. And that's important because it behaves a little bit differently. You can't have friction unless there's another force trying to make something move. So friction is a reaction to whatever other force is pushing or trying to make something move. And it always works against you. If you're trying to push something to the right, the friction will act to the left. It tries to stop or to prevent whatever it is that you're trying to make move. Let's try to envision why there's friction at all, first of all. So let's think about two surfaces. Let's think about a box sitting on a tabletop, like this. Now, in our macroscopic world, we look at the box and we think that it's actually in contact with the table. But we know that it's actually not, right? We know that if you were to get a microscope and look at the space in between the table and the box, you would see the bottom of the box, and although cardboard looks smooth, it's not very smooth under a microscope. So it might have a very rough sort of surface. And then down here we would have the table. And tables look smooth too, to our eyes, but under a microscope, they're not super smooth. They're actually quite rough. And so you might see another rough surface sort of underneath it. Now, if this is the box up here, surface, and this is the table, or the ground, or whatever, and there happens to be a relatively large space between them. Remember, this space is caused by the electrons on the outside of each thing repelling each other. What would happen is you would get forces that are primarily vertical. Okay, the electrons will push up and down and sort of prevent the surfaces from actually touching. Now we know this already, but look what happens if those surfaces get closer together. Instead of these red vertical lines right here, watch what happens if I draw the same two sort of squiggly surfaces, sort of like this, but now closer together. So the other one will be sort of nestled kind of like this underneath it, so that the space between them is smaller. Let's write smaller space between. Okay, this would occur if the box was very heavy. There'd be more gravity, which would pull it down closer to the tabletop. Now let's look at what happens. What happens here is we start to see forces that are going to be kind of sideways. There are components of the electron forces repelling that are no longer straight up and down, but are sort of sideways-ish. In other words, the force has more horizontal components like this because the little hills of one surface are tucked into the valleys of the other. And when you try to slide it across, you'll get more of these sort of horizontal components. So we'll write that. The closer the surfaces are together, the more horizontal, sideways, components there are between them. All right? Actually, we should probably say the more horizontal components of the force between them. let's change the grammar here. Sorry, it's last block and I'm a little tired. Let's write this as there are more horizontal components of the force between them. That makes more sense. Okay? So if you look at the two pictures, here, up above, it's uppy-downy forces only, which cannot affect left and right movement. But as you get the surfaces squished together, these little components that are a little more sideways can now begin to affect the sliding of an object across the surface, backwards or forwards. And that means that this creates the frictional force, or the resistance to motion. So that's one of the things. The other thing, of course, would be the degree to which the surface was bumpy. If you had a surface that was very smooth, without very many bumps, even if it's close together with another surface, there would be far fewer horizontal components of that force in here. There's very few hills and valleys to bump up against each other. So there are two things that matter. One is, I'm going to put friction depends on two things. One of those things is how close the surfaces are together. In other words, another way of saying that is how, it depends on how much force there is. Let's put how much force there is pushing the surfaces together. So let's talk about that idea a little bit more. How much force there's pushing the surfaces together. Let's draw a couple of pictures just to get our heads around that. If we have a box sitting on the floor, then the force of gravity is pulling down, right? And the normal force, the force of the ground, pushes back up. You've seen that already. If we draw a picture of, we did the fridge magnet, the fridge and the magnet on the side of the fridge, there would be a magnetic force pushing in, let's call that F mag, and then there would be a normal force of the fridge pushing back. We saw that the other day too. Even if I were to take my hand and push against the wall, try and draw my hand here pushing against the wall, there. If I push into the wall with the force of my hand, then the wall pushes back with what we call the normal force, right? When you look at all these pictures, there's three different examples, but they are all forces that are squeezing two surfaces together. A box on the ground, a magnet on the fridge, or your hand on the wall. They're all different. One is a magnetic force, one is a gravity force, one is a force of a hand. So it's easier, though, for us to look at what happens in reaction to this. Is there's a normal force in each case that is equal and opposite. So if we want to talk about the force that pushes the surfaces together, rather than talk about all these different forces, no matter what force you use to apply, there will always be a normal force, and that normal force represents the force between the two surfaces. So the normal force becomes the force between two surfaces that we can use to help us with friction. So that's the first thing that matters. How much force is squeezing the surfaces together. The other thing that matters, to be said, is how sort of smooth, the smoothness, I guess you could say, of the surfaces, or the stickiness of the surfaces. Some surfaces are rougher than others. We can see that in a macroscopic view with our eyes, obviously. Sandpaper is rougher than glass. But even on a microscopic view, you can see even more distinguishing differences between smoothness. You can see something that's really super smooth, where all the molecules line up very easily, Others are rough. Paper, for instance, looks smooth to us, but it's rough under a microscope. So the smoothness of the surfaces, and this is a microscopic smoothness that we're talking about. And the way we describe it is with something called a coefficient of friction. Coefficient of friction. And it's given the symbol mu, which is a Greek letter M. Looks like a funny little scripted M. And the coefficient of friction is just a number that is the comparison of two surfaces to see how slippery they might be. Commonly, you will see mu's anywhere from 0 up to about 1-ish. They can be more. They could be 2. They could go. There's no limits. But it seems that when we compare surfaces, 99% of the things we encounter in everyday life will have mu values, 0.1, 0.4, 0.8. Like the rubber tires on a road are about 0.8-ish, whereas walking across some ice in the winter might be more like 0.1 or 0.2. The lower the number, the slipperier the surface. Higher the number, the less smooth and the stickier it would be, the more friction you would get. So mu can be any number. The other thing that's interesting about friction and mu is that there's actually two kinds of friction. One is called static friction, and this is the friction that exists between surfaces that are not moving against each other. Static friction. Things that are not moving. And we usually use a little mu with a little s to show that coefficient of static friction. The other possibility, though, is to have something called kinetic friction, which is the friction that exists between surfaces that are already sliding against each other. Right? So when you take a run at some ice and you go sliding across the ice, as you are sliding across the ice, you are moving. Your feet are sliding across the ice. So it's kinetic friction that you are dealing with in that situation. But if you just have a very big, heavy box in front of you and you're trying to push it and it's not moving, and you're pushing on it, but you're not strong enough, and it's not moving, it's static friction that you're fighting against. Now, the funny thing about this is, first of all, static friction is always greater than the kinetic friction between surfaces. It's always a little harder to make something start moving, but then once it's moving, it kind of is easier to push it along. So the static friction is always a bit greater than the kinetic friction. But the beautiful thing is that we generally just use a mu without the s or without the k. So we just see mu. And we understand that whatever the scenario is that we're talking about, that's the proper mu for that scenario. If it's a moving scenario, it would be a kinetic mu, and if it's a stationary one, it would be static, but we don't distinguish. We don't worry about this. So it's something to keep in the back of your head, but it doesn't really affect your problem solving all that much. Unless you have a carefully contrived problem that's specifically trying to point that out, which we won't worry about just yet. So, let's summarize what we just said. Friction depends on, and it would be on the smoothness of the surface, smoothness, multiplied by the force pushing surfaces together. Those are the two things that matter. So if we use a little bit of mathematics, we can write the force of friction equals the smoothness, or the mu value, multiplied by Fn, the force pushing the surfaces together, which is the normal force. So it's a very easy little equation to calculate, but it's a pretty tricky concept to get your head around. All right, let's do an example. You okay? Did you catch up with the writing there? Everybody good? Okay. Let's do a couple of examples to see how this formula might work. So here's example 1. Let's put a box say it's 20 kilograms and it's sitting on the ground. Okay. What we want to know is, what is the maximum force of friction between the box and the ground if the mu for these particular two surfaces is 0.4? Question mark. Okay. What is the maximum force of friction between the box and the ground if mu is 0.4? Well, we can figure out the normal force by looking at the picture and labeling the force of gravity here. And then the normal force would be here. And we need the normal force because that's how we calculate friction. So we could do this one in our head probably, but let's do it with the net force equation just to practice. F net y is Fg plus Fn, right? All the uppy down arrows. And F net is equal to ma, according to Newton's second law. Fg is mg, and then Fn we put here. So remember our equation for force of gravity, it equals mg. Okay? And then if I just kind of go over here and finish that off, we can put the numbers in at this point. The mass is 20 kilograms, so m. Now let's think about the A. It's a box that's just sitting there. It's not moving, so it has no acceleration. mg is the force of gravity. Now I have to remember at this point, when I put in the numbers, I also must put in the correct signs to show the directions, right? So it's a downward force, so now I'll put in the negative, I'll also put in the 20 kilograms and the 9.8. And then what's left is Fn, and we can see what's going to happen here. 0 equals 196 newtons negative plus Fn, and the normal force comes out to the same, 196. But we knew that because we knew that the forces had to be balanced, right? So we have the normal force. Then we can just continue with our new formula, which I'll write green here. The force of friction equals mu Fn. So the mu was 0.4. That's how rough the surfaces are. And the normal force is 196. So that means that if I multiply those together, the force of friction, 6 fours are 36. Sorry, wait a minute. 6 fours are 24. Let's do that right. I'm thinking ahead. 6 fours are 24. 36, 37, 38, 7.8. 78.4. Let's put the decimal in the right spot. 78.4 newtons is what you would get, I think. Okay? When you multiply that, somebody double check. Okay. Now that's the maximum force of friction. And it's important to understand what that means. The maximum friction. Because friction is a reaction force, it doesn't always push with the same amount. Let me show you what I mean. So let's draw this box. This very same box. And we said that the friction is 78.4 newtons maximum. So I want to imagine if I go over here and I push on the box with 1 Newton. 1 Newton. Okay? In fact, if I draw that on the other side of the box, it might be less confusing. So we'll draw it as a pulling force of 1 Newton. So what will happen to the box? Well, the friction will look at me and laugh and say, well, you can push with 1 Newton, but I can push with 78.4. But it won't push with all that. It'll react to me, and it'll push backwards with 1 Newton, the force of friction, because the box won't move. Friction can't make a box move. Boxes don't just suddenly fly backwards because of friction. So the friction only pushes back as much as it has to react to what I'm pushing with. So now, If I step up the game and I say, okay, friction, I'll push with 60 newtons of force. Well, the friction says, no problem for me. I can also match your 60 newtons, and the box doesn't move. So you see how the friction only pulls or pushes in reaction to what is being pushed against it. It never pushes with the full amount. That's why this is the max. Now, watch what happens. If I push with exactly, or pull with exactly 78.4 newtons, the friction says, well, I can still hold you back. But now the friction is getting a little nervous because it knows that if I pull with any more force, even a fraction of a newton, friction will have passed its maximum and will not be able to hold me back, and the box will begin to move. Right? So that means the friction will just continue to match my force up to the maximum of 78.4, at which point it will stop, or not be able to push anymore. Okay, let's do a few examples where something actually does move. So, let's take the same sort of idea. You're pushing the box across the floor. If the mass of the box is, let's say, 40 kilograms, right? The mu, 0.3 this time. It'll be a nice shiny hardwood floor, a little slippier maybe. The question we would like to know is, what force must you push with to move the box? Now here we have to think about something too. There are two ways to move a box. So let me just draw two scenarios. One, the box starts off at rest and we push like crazy, going faster and faster and faster and faster. We accelerate the box along the floor. But that would be stupid. Nobody does that. Nobody pushes things like that. Generally what we do instead is we push things across the floor at a constant speed. So if the question doesn't specifically mention an acceleration, you can assume that we're pushing it at a constant velocity. So in this question here, what force must you push with to move the box? What we mean by move the box is move it at a constant velocity, not an acceleration. Okay? So let's figure that out. I'm just going to erase that so it's not in our way. Okay. All right. So we look at our picture. We're going to put our free body diagram over here with our forces on it. Force of gravity, down. Force of the normal is the table pushing up. Up. Right? Question, Chief?
Yes, sir.
What is it?
Friction be considered like the acceleration?
Can friction be considered the acceleration? No. Friction, well, the deceleration. Friction often causes deceleration. It isn't the deceleration, but it might be the cause of it. What causes deceleration is when you have a net force in the opposite direction that you're moving. And one of the ways of getting a net force in that direction would be, could possibly be friction, right? But there's other ways of that happening too. You could push something in the opposite direction it was moving. So friction plays a role in determining the net force, which determines the acceleration, as we're going to do in this example. So watch this carefully. We have to now add the force that we're going to use to pull or push the box. So I'll call that the applied force, right? That is this force right here, the force that we're using to move the box. Then we have our new friend, friction. Remember, friction opposes motion, so the friction would have to work against me and pull backwards, or against the motion of the box. So now we have a more complicated free body diagram with all these forces in it. But we can still separate the uppy-downy vertical forces and the lefty-righty horizontal forces, which we will do. So we'll start with our F net Y. In this case, the two forces that are vertical are gravity and the normal force. So gravity plus Fn. Now, this is just the up and down motion, remember, the vertical motion. So F net is always ma. Gravity is mg, and the normal force is just Fn. The mass of this box is 40 kilograms, but the acceleration up and down is 0. So that's a 0. I'll put here negative for downwards, because gravity is downwards, 40 for the mass and 9.8 for g, plus Fn. And so if we just slide up here, then we have 0 on the left side equals 4 8s are 32, 4 9s are 36. So 392 with one decimal place, 39 point, nope, my mistake. We got the 0 over there too, it's just 392. 392 newtons is the gravity negative plus Fn. Move it to the other side, we now know what the normal force is. So our F net Y tells us that. But that's not the answer to the question. That's just the normal force. To do the next part, we go to F net X. F net X is the sum of all the sideways horizontal forces in the picture, and there are two of them. There's the applied force in blue and the frictional force in green. So I'll put those two forces in as my sideways forces. F applied plus the force of friction. And then we do the same thing. F net is ma. F applied is kind of what it is. And the force of friction, we said, was mu Fn. Remember? That's our new one. So that replaces the force of friction. Now I'll put in the numbers and the signs all at once. 40. Now we have to think about the sideways acceleration. We just finished saying, though, that when we move a box, we don't accelerate it. We slide it at a constant speed. So there still would be an acceleration of 0 sideways, because we're talking about constant speed motion. F applied. And we now have a negative sign, because the friction arrow is pointing to the left, the green arrow, right there. And the mu value is right here, 0.3. It was given in the question. So we'll put the 0.3 in after the negative sign, and we have the normal force because we figured it out in the F net Y, right there. So we'll bring that down and put it here as well. And now we have everything we need to figure out the force we need to apply. 0 equals F applied. Notice how the answer we're looking for pops out. 3 times 2 is 6, 3 times 9 is 27, 11, 1 decimal place, so about 117. Move it to the other side. That would be the applied force necessary to move the box. Yep.
Level 3.
Oh, this is definitely about a level 2-ish here for sure. You'll see what happens in level 3 and 4 once we get the hang of it. It seems like a lot of work, but it's actually not that bad. Okay. Whoops, I don't need that. All right, let's do another example while we have the time. The more we do, the better. So, let's do an example this time where there is an acceleration. All right? So let's imagine that you're a bartender. Okay? So you're standing behind the bar, and there's a mug here. And what you're going to do is you're going to accelerate the mug down the bar to the customer who's sitting here on the bench waiting for his beer. So you're going to slide this mug of beer, but you're going to accelerate the mug of beer this time down the tabletop. Okay? So you're going to accelerate a mug, and we'll say that's about 0.3 8 kilograms. I guess we shouldn't write mug, we should write mass. Mass will be 0.8 kilograms. I'll give you a mu value for the tabletop. We'll say 0.3. And what you want to do is you want to accelerate this little glass down the tabletop at 0.5 meters per second squared. So the question is, what force must you push with to make that happen? So again, we're looking for the applied force. But this time we have an acceleration. And you'll notice that not much will change. Okay, we can start with, there's 3 things we do. We do a free body diagram first. Here's the table, here's the mug. 0.8 kilograms. And we draw our arrows. Force of gravity will be down. The normal force will be up. And then we do the horizontal forces. You are going to push the glass with an applied force, and the friction force is going to work against you or against the cup to try and stop. So, same thing, F net Y. Well, there's a normal force up and down, and there's a gravity force. So you don't have to think about this, you just look at the picture. So there we are. F net is MA. Fn, and then the force of gravity is mg. Okay? When it's time to put in the numbers, that's when I put in the signs as well. So now let's do that. Numbers and signs. 0.8. Now, be careful. Remember, this is the y. So this is y acceleration. We want the cup to accelerate, but I think we all realize this is not up and down. This is an acceleration that's going to be sideways along the bar, right? So that's not the A for this. That's going to show up in the F net x equation. So our up and down acceleration is still 0, because the mug is not going to accelerate up into the air or down through the bar. Minus, because of the downward gravity force, right? The arrow is down, 0.8 times 9.8. So 0 equals Fn minus, and this is going to be 64, 72, 78, 7.84. Okay? And so 7.84 goes to the other side, and that is the normal force. Did I do that right? I think so. Okay. Then we do F net x. F net x. To do this, we look at the picture again and look at the sideways forces. Well, there are 2 of them, F applied and the force of friction. So we'll put those 2 in, F applied and the force of friction. F net equals ma, Newton's second law. F applied is what we're looking for, and the force of friction is mu Fn. Just like before. Now we put in the numbers and signs. The mass of the cup is 0.8. This time we do want the acceleration. This is where we will use that number, that acceleration of 0.5. That's the sideways acceleration. So that's the only difference. Last time we got a 0 here. This time we're going to put 0.5 in here, because the question said so. Minus, because of the left-handed arrow, right, pointing left, mu, what did I say, 0.3, I think? And our normal force we borrow from the other equation, from the F net y equation, 7.84. And then we just do the math. This will be 0.4, half of 0.8. F applied. And this would be 3 4s are 12, 3 8s are 24, 25, 25, sorry. Just carry the 1. 23, so 2.352, I believe. Is that right? Okay. So then what we have to do is move it to the other side. And we'll add it on the other side because it's negative So it'll be 2.75-ish equals F applied. And you notice what this means in English. This represents the force of friction. See, right up here. Traced it all the way down to there. This, over here, represents the force required to do the accelerating. So we trace that down. And what the math is telling you is if you want to accelerate the mug, you need enough force to beat the friction, plus enough force to do the accelerating. And the two numbers end up being added together to get you the answer that you need. And of course that would be newtons of force. 2.75 newtons is what you would use to accelerate the cup. Any questions about that? All right, we have time for one more. So what I'm going to do now is I'm going to show you how sometimes friction can mess you up a bit. I'm going to change this question up. Let's say it's, I guess I can't, my page is at the end of my page here. So maybe what I'll have to do is, I'll have to do a second video. Oh, I know what I can do, wait. I can just go to the top here. I can just file, new, save, no. Okay. Let's say you're back at the bar. This time you want to change it up. It's late at night and everything's going kind of slow. So somebody orders a beer. Instead of sliding a mug down the table, you're going to slide a 400 kilogram gorilla. That should certainly elicit some sort of response from the half-drunk people in the bar. So what would change? Well, the mass of the gorilla is obviously way bigger. The coefficient of friction between a gorilla might be he's a little hairier than the box, so we'll make that a 0.5 just for fun. And what else do we need to know? This time we won't accelerate the gorilla, we'll just slide him. So how hard do you push this gorilla to slide him down, and we'll say it's a constant speed sliding this time, so there won't be an A. How hard would you push this gorilla? Actually, I changed my mind. Sorry, you probably wrote that down. Let's make it, to make this mistake show up better, let's solve something else. Let me say that you can only push with a certain amount. Okay, what I'm going to tell you this time is that you can push with an applied force of 1,500 newtons. That's as strong as you are. All right? I hope that'll work for that number. Let's go through the scenario. We quickly draw our free body diagram. FG. Fn. I'll squeeze Fn up here. The applied force and the frictional force. And we go to town. Okay, I do want F net Y, so we'll start with F net Y equals Fg, Fn. I'm going fast now because we kind of know what we're doing here, right? Mg, Fn, mass 400, and we decided that we just want to slide at constant speed, but this is Y anyway. This is up and down, so it's going to be 0 no matter what. And then 400 times 9.8 plus Fn. Okay, so now I'm going to check my numbers here again. I think I might have made a mistake. 400 times 9.8 equals... Nope, that's good. Okay, so we're all right. So this is 0. This comes out to 3920 negative. I forgot the negative sign there. See, that's gravity, so I'm going too quick here. I better slow down. But we get the idea that 3920 is the normal force of the ground pushing up, the force between the surfaces. Okay. Then we do F net X, and this is where our problem will show up, so watch carefully. There's an applied force sideways, and there is a frictional force sideways. MA equals F applied. Now we can put a number for this, can't we? Because the question said that we can push with 1,500 newtons of force. So let's use our 1,500 newtons of force, and let's see what happens. This will be mu Fn. The mu is 0. Did I change it? For the gorilla? 0.5 And then the normal force is 3920. The mass, of course, was how much? 400 kilogram gorilla, but if it's constant speed, this is all going to work out to 0. And I think this comes out to 3920, 1960. Okay. Now let's say that you were solving, let me go back right to here. Watch what would happen if you just followed the math and did this. Let's say this question asked you, I didn't really specify what the question would be. What if the question asked you to find the acceleration of the gorilla? Then you wouldn't know it was constant speed. And you might think, oh, okay, so we're going to solve for A. So you'd leave the A here, and you think you could solve for it, right? Looks pretty simple. So watch what happens. If we solve for A, we get 1500 minus 1960, which is negative 460. And this is the part you shouldn't write down. Stop writing, but watch. Divide that by 400, here's what you would get as an answer. And because you got an answer, you'd think, oh good, I'm correct. But there's a problem with this answer. What's the problem? It's negative, which means it's left, which means our gorilla is going the opposite way you pushed it. That doesn't make sense. And the reason we went astray is because right here, at this point in the question, you need to always keep your eye on this friction force. Look how much the maximum friction can be, and look how much you are pushing. Clearly, this friction can always match you. The friction is not going to push with 1960 and make the gorilla go backwards. But the friction is going to say, well, I can push with a maximum of 1960, but I will react to you, and I will push with the 1500, which means you will not be able to move this gorilla because the frictional force is too strong. So you always have to keep an eye on the friction, and don't let it fool you into thinking you can get an answer that's backwards or weird. Okay? You have to kind of watch with your eye on what's happening on this part of the expression. And if that happens to be bigger than the forces that are being applied, the object can't move, and then you can just jump right to the answer of A equals 0. So sometimes friction can be a little bit tricky. Other than that, tomorrow or the next day we will do more examples and look at some of the level 3 and 4 type questions that are a little bit trickier, and but it shouldn't be too bad.